how have you been, especially as it relates to your experience in these classes? If you like, you could type your feelings, your sentiments, your thoughts on the chat there. We've gone halfway or more than halfway through. We've completed the data structure, and now we're going into algorithm. So I'll briefly share my screen while with some comments in the chat session. Okay. Okay, I'll share my screen now. Let me see what I have here. Okay, can you see my screen? Data structures and algorithm week 7.
Yes, we can.
Okay. All right, good. Good. Thanks for the confirmation. All right, so searching algorithm is one of the most important topics in computer science, generally with information processing. Later on, as you do further research, you find out that is at the base of current innovations in artificial intelligence, machine learning, and other variants of that topic. Okay, but we are not going to that level today. We are still looking at the fundamental, at the atomic level, what makes up a set of instructions or commands, rules, and concepts that are used for searching. So today we'll start with recap of what we've learned so far. Then we do a little bit of an introduction to algorithm. Ideally, we're supposed to have sorting comes before searching. So to put the discussion today in the proper context, I'm going to just speak briefly on sorting, especially with how it relates to searching, and then we'll continue from there. Next week, Sheyi will go deep dive into sorting, but just note that just invert the order. Sorting should come before searching, and you see how that works later on. So then from there we'll go into the actual meat of the discussion. What have you learned so far? This is a summary of it in a nutshell. Starting with arrays all the way to graph last week. All right. In between those two, we've looked at a linked list, stacks, queues, hash tables, heaps, trees. And you'll find that today we've talked a little bit about searching while going through this data structure. That is one interesting thing about data structure and algorithm, that there is no way you talk about the structure that you do not make some mention or assumption of the algorithm most optimal or efficient for that structure. Okay, so keep all this data structure in mind. Okay, it is just clear that if you can have a sticky note like this on your computer, on your bedroom wall, wherever you think you will need this information to just be handy for easy memory refresh, yes, uh, keep them in mind. This covers everything about structure in terms of the fundamental concept, what is out there. Okay, if you see any structure or that is not mentioned here, let us know. Okay, but these are generally the major structures. And you'll find that all through the past 6 weeks, a major highlight of what we've mentioned about data structure are somehow around the items I listed below. Key important thing you should know is that your data does not necessarily depend on structure. All the structures we've discussed can be used to manage or store any data or values or information. Okay. The choice of the particular structure you use will be determined by other considerations such as your use case scenarios, functionalities of your applications, the kind of efficiency or runtime that you want your users to have. Okay, and at times the storage mechanisms, how you are going to store the data in your database. Okay, but note that all these structures, all the structures can be applied to any data. Uh, at the fundamental level, we talked about array being an important data structure, and on the array structure, you can pile on more complex structures like your list, your linked list, your stack, your graph, matrix, and all. Okay, so mastering the use of array is very important. Okay, very important concept that you need to know, and as you also job search and prepare for interviews, is important you know how to be able to manipulate an array in case you go for a practical test, all right? Or you're given any problem scenario, you find out that you could just quickly begin to structure your data in the test as an array and manipulate the array to get whatever you want. And another key thing in the data structure so far we've mentioned have to do with traversal or going through your items, whatever, irrespective of the structure you're using. You'll need to be able to iterate. That is, you go through all the items one after the other from the beginning, starting with index 0 to n. Okay, n minus 1. Okay, so being able to traverse any data type, be it queue, stack, list, graph, tree, that is very, very important. Okay, we also pay particular attention to changes. Okay, change operations such as item insertion, deletion, maybe update, but insert and delete are major operations you perform on your data that have at times some wide implication. Implications such as data may need to be relocated in terms of an array, in terms of a tree, data, your items may need to be rebalanced. Okay, so attention to not just the storage, but operations such as adding a new item and deleting a new item and keeping the shape, keeping the data in that shape, all right, to make further operations like search important. So at the base of this discussion is that search is an essential reason for maintaining your data structure. Okay, it should be at the back of the mind, and you'll see how that connects with this today. All right, but before we go further, so we quickly just talk about algorithm. Okay, there'll be further classes on algorithm. I think that should be week 9. Yeah, after sorting, we'll have the remaining classes on more on algorithm with specific mention for divide and conquer, and then dynamic programming. Okay, so but just note it about algorithm. Algorithm is the specific procedure that is taken to solve or perform a computation, calculation, data processing, or whatever information processing, like automated reasoning. So as a procedure, is a set of steps, all right, from a starting point to the end that solve a problem, okay, or arrive at a solution. It's a finite set, okay, which means that it has a beginning and an end, okay, a finite set of commands, rules, or instructions to perform an operation. So your operation could be anything. It could be search. For our purpose today, we are talking in the context of search. It could be a search. It could be an insertion, a deletion. As you saw in the previous classes, when we add item or to add item to a tree, there is an algorithm for that. You also saw that last week. What does it take to add an item to a tree, a binary search tree? What does it mean to, how do you go about adding an item to a linked list or to a matrix? Okay, the step you take to add item to maybe or maintain your hash table. Okay, so know that algorithm is your stepwise procedure. It is problem specific or domain specific. What that means is that this set of finite principles or rules address specific problem or instance of a problem. Okay, so it may not generalize to other problem scenarios. It will not be optimal for other problem instances, but for the particular problem that it is built for. Okay, so you can't use the greatest common divisor algorithm to solve this Fibonacci sequence algorithm. All right, so they can't be moved around. So they work with the idea that, or with the assumption that the data being worked upon is structured in a particular way. All right, so your algorithm is tightly coupled with your data structure. Oh, okay. So this is why this is we've emphasized this again and again about the relationship between structure and algorithm is the same as the relationship between time and space. All right. You cannot separate time or your concept of time from the space, the environment you are in. In this case, we are talking about environment at the planetary or solar level. Okay, so it's the same thing with data structure algorithm and algorithm. The algorithm is tied with a particular values. It makes assumptions about the data it expects, and if that data assumptions fail, then the algorithm will fail or will perform badly in terms of the runtime. The algorithms are usually written in pseudocode. Uh, it could be as simple, it's a list. Remember, it's a list. So it can just be a set of descriptive words, okay, usually numbered to arrive at a solution. Okay, so it's not language specific, it's not programming language, meaning if you put it in your development environment, you'll get those squiggly red marks. All right. Also, worthy of note is that your algorithm is language independence. So you could pick any of the algorithms we are talking about today and implement them in your language of choice, your programming language of choice. Okay, so you it's usually not said that, oh, this algorithm only works with Java or with Python or with C Sharp. Okay, performance may differ across platforms, across languages, but algorithm should be implementable in every language. Okay, so that let's note that about algorithm. It takes an input, which is your data, and then provides an output, which is the expected result. Okay. Just one quick note on the algorithm discussion is, all right, the problem that is solved by an algorithm must be well formulated. So when you practice solving tests on lead code or HackerRank or any other platform that you use, pay attention to the wordings. You will find that the tests are worded usually in a very clear and concise manner. All right, they contain as much information as possible, even to the extent of providing sample data, sample result. Okay, maybe 1, 2, 3 to cover the full scenario. Okay, so that you should be able to, provide a solution to that. So the problem must be clear. If it is fuzzy, then your algorithm is going to struggle. You are actually going to struggle to come up with a fitting algorithm if the problem statement is fuzzy. Okay, and once the algorithm is created or defined, once it's defined and implemented correctly, it should be consistent for every problem or input instance. Okay, that is, if you are given the same values, remember your data assumptions, you're given the same values or the same, you are given a value in the range of possible values. Okay, it should produce the right result. Every time it should be correct, it should be consistent. Okay. So usually in the problem statement of your algorithm questions, you'll be given a bound So a bound such as the highest value that your solution should be able to work with. So in some cases, you see something like you should be able to work with a given number, say 10 raised to power k. K could be 5, okay, which means that if you resolve that exponential equation, your any range of value given around that, okay, should be allowed by your program, and the algorithm behind your program should be able to produce that output. So you are always given that bound, and as long as the bound is not exceeded, your algorithm should be stable or perform correctly. So that also puts a limit on the scope of your algorithm. All right, your data, your problem instance, the range of values or possible values or allowable values, okay, determine how far your algorithm can go. It determines the limit of your algorithm, okay, and within that limit or within that scope, we can begin to compare algorithm that, okay, if all these data are given the same, if all these programs are given the same algorithm, which one is faster, which one is slower, dependent on how each algorithm arrives at their solution. So, okay, so you always have to think about speed or runtime. And that is why we talk about the big O notation. By now, you should be comfortable or used to the big O notation in terms of when we say big O of n, big O of log n, or n times log n. It could be described as maybe your algorithm runs in linear time or in constant time, quadratic time, or exponential time, okay, which would be really, really bad. Right. So behavior of the algorithm based on input size is also very important. So, okay, so size is important. Usually in your practice test, you are given an input size as part of the information. So we'll move on here. This is just to project the relationship and difference, the two sides of the coin, each side being data structure, one side being data structure and the other being an algorithm. So where your structure focuses on inputs, your algorithm focuses on output. Okay, we'll move on. As I mentioned later, we'll talk more about these techniques for algorithm implementation in week 9 class. Greedy algorithm, divide and conquer, and I think week 10 should talk about dynamic programming or a little bit about dynamic programming. Yeah. Before we go further, so I'll just quickly make this case for sorting. Your data is important in terms of how they are stored. And to begin to do a stretch or a find operation, we have to pay attention to the order of the data. So the order in terms of the arrangement or whatever is used to arrange the data is very important. Okay, so sorting and searching go together. Without sorting, what it means that your search will likely be sequential and time consuming. When we say sequential, it means we'll find later, we'll go through each item. one after the other, the whole record. We have to go through everything, and that has its own implication. Okay, there's usually cost involved in sorting your data, because in some cases it takes additional resources. You may have to maintain an index table for binary search, and using hashing. You have to maintain a kind of table of index. All right. So sorting costs more in terms of storage, and at times it has additional runtime to begin to search. But then it needs to be fast so that it does not become a problem to your solution. Okay. Your data may have to be pulled in whatever order they are stored, arranged in a specific way for efficient searching. Okay, the speed of your sorting is affected by usually how you go about comparing each element to determine which ones should swap position or place for another. Okay, and the number of exchanges that actually happen, exchanges such as you replace item in a particular position with another item. So the number of such exchanges will determine the speed of your sorting. This is just a quick talk on sorting, just to note that it is important to determine the types of algorithm or the type of search algorithm you will use. In some practice tests, you are likely going to be given unsorted data, all right, and be expected to work with the unsorted data as it is. In some cases, you're expected to sort those data before you begin to work on them. All right, for each case, in each case, I think you will usually be told the expectation. Okay, now we go into search algorithm. Then in talking about search algorithm, what comes to your mind when you think about search? Let's see. When you think about search, is there any particular thing that comes to your mind? You see the way I have the chat on. Okay, you can type messages in the chat section. Okay, someone raised a hand. Ifeanyi, do you want to type your message?
Okay. I just wanted to speak on searching.
Okay.
You asked what comes to mind for searching. So I would say position, using position or a location. That's
using
what I
a
think.
position or location. Okay. Okay.
Thank you.
All right. Thank you. All right. Fair point. Using a position or location. That assumes that you already have information about the position and location. In that perfect condition, there is no more need for search, okay, because you already know where it is. All right. So that's why I said it's a fair point. Usually, life is not that perfect. You don't know the location, you don't have the position, and that's why we spend our time searching. So I have a couple of other suggestions here. Looking for an item in the list of similar items. Okay. Yes, looking for. That's a keyword there. That's good. Finding a value in the data set, yes, good. Finding, yes, is a key term there. Search is basically looking for a referenced item or data. Yes, uh, looking for is very important there. So the key words among all these suggestions is the fact that you are looking for something. Okay. And this is an important aspect of search. No, all right. But before you think about search, remember the key point on data structure. Think about your data structure. So think about the uh, movement, the kind of mobility you are going to have around your data. Are you moving upward, downward? Are you moving left to right, right to left? Okay. Are you moving in a kind of a pattern that goes from up to down? And as it goes from one layer to the layer below or above, it branch off into another segment? Are you going, is your search going through a kind of cycle? Is there branching in your search uh, implementation? Are you moving in a maze? Okay. Are you moving in a maze? Are you on on a checkboard, uh, moving things around your checkboard? So you always have to think about uh, the shape of your data and then have an intuition, like have a picture in mind of how your search implementation is moving, the kind of movement. Okay. These shapes here are very simplistic. Okay, but you should have this kind of thing in your mind and they form the kind of algorithms we talk about on that search. Have the picture. So how your data is arranged already places that limit on your algorithm. Okay, it already does that. Okay, so think about the movement as you search for data. Are you going up and down? Are you moving sideways? As you go up and down, are you branching off into different sections, different subsets of data? Are you moving like in a matrix? So, okay, where you move through different rows and columns. So, just for everyone to have that kind of picture, think about it carefully in your mind. So, this quotation is very instructive. Okay, of all the tasks that applications do, searching is the most time consuming as well as the one required the most. So this is why we said that it is an essential consideration for your data structure. Okay, is the most important. And if you think about it in bigger context, we spend most of our times, most of our lives searching for answers. We get questions for a good number of them. Some of them can never be answered. We spend time searching for things, spouse, job, friends, your car keys, your phone. You dropped it somewhere. Now you're looking for it. You search your drawers, looking for an item, and in the process, you go through certain thoughts. Certain thoughts go through your mind as you perform your search. Okay, it is the same in computing. Okay, so search is very, very important in computing. It is the big money spinner for companies such as Google today. I mean, like Google is practically built on search, right? Okay, so it's very important. And solving that problem in computing at the time Google did uh, was a breakthrough for the company. Today is still a big money spinner for the company. Okay, so search is very, very important. Google is just one of them. There are other many applications that we use today. In fact, virtually all applications we use today rely on one search or the other, at least one search implementation or the other. You want to come here to on your screen, you want to find something, say, I think it should be find. This find and replace is based on search implementation. Okay, so irrespective whether you can say this is a presentation, we are building an application, we are collecting the data, but we cannot search that data. I mean, it sounds absurd. Okay, as long as you collect data, you should be able to search that data. You should be able to find and look for eventually. Once you search and look for it, you should be able to get the position if it exists. If it doesn't, you should be able to reliably say, no, uh, cannot find this data. All right. So search is very, very important. It's also time consuming. Okay. Very time consuming as much as is required. All right. So we are always solving the problem, and we haven't yet solved the whole problems or challenges posed by the need to search. Okay, so it still continues, though, as we see later, we have an efficient or some efficient methods for resolving that conundrum of search. And as we go into search, note these key terms: your data, all right, which is stored in your particular structure, may be ordered or unordered, that is sorted or not sorted. You'll find in some books, articles you read, uh, the use of the word key. Okay, so your key is what you use to identify your data or a particular record. Okay, so when you search, when I come here and I do a find, I'm searching with whatever I'm searching with, okay, usually would be, some will call it key. I'm looking for this. Okay, you type in whatever there, and then it is compared with data in your storage, and then the data is returned. Okay, in some cases, your data is maintained separately from key, and we'll see that key value relationship later. So note that your values or your data could be stored differently from your keys. Some aspect of your data, some of your data, or some of your records could be made a key. A typical example of that will be in a database record scenario where you have a set of columns, and one of the columns, we call it primary key. All right. So the concept of a primary key is in that database example is fundamental to search. It is built with search in mind. That when we want to look for this record that is made up of a set of columns like student number, student name, uh, student age, and student class, we will use a key like the student number to search. All right, so just for you to note that term. And in some cases, when there's a successful match, you say there's a hit, and where when it's not successful, we say there is a search miss. Okay. You will come across these terms more in search when you go into search implementation, search algorithm and implementation, DFS, BFS. I think that was mentioned last week. Depth first search, breadth first search, binary search tree, binary heap. These are key points you should know, key terms you should know in search algorithm. And then, of course, you should pay attention to the time complexity of your search algorithm. Okay, so these are important. Then talking about the key value relationship or dichotomy, your values could be stored this way, where in actual memory, you have these data. So these are your data. Okay, at times for efficiency, another table, some call them symbol table, some call them keys table, some call them indices. Okay, that's the idea behind index. A separate table is maintained to store your keys, so that when you're looking for a record, say you're looking for D, it will search. If a user types D in your program, the application do a lookup in an index table like this. And so, okay, D is in this position, and then use that to pick this. This works with the assumption of a hash table. This is how hash table works essentially, where the value given is taken through a hashing operation, which generates a hash code. Okay, that hash code gets a position. So this value is in this index. Okay, but whether implemented with hash table or not, just note that in some cases, how your data is stretched out, stored, could also require storing separate keys for search. I will talk about this when we get into the binary search tree. Oh, okay. And okay, I'll come back to this diagram then. Okay, so few quick things to note on searching. We can't overemphasize this. Understand your data type, okay, and then content. Look for what kind of data do you have, all right? For instance, if you are looking for words when your data contains numbers already, you're going to get a lot of miss there. Okay, unless you're doing translation, type conversion, which again is not optimal. So note the kind of data you're working with. That's very important. Understand the use cases of your search. So at the beginning, when the data is being structured, it should be clear the business purpose, the functionalities that we expect from this data storage. So when we're storing this data, we're storing them for ease of navigation later on. Are we collecting data in such a way that we can use them for path finding, path analysis for navigation purpose? So at that point, at that earlier stage, graph data structure should be at the forefront. Okay. it is not efficient to store such data as a linked list. You're going to have performance problem. Okay, it's not efficient to store such data in, say, queue. You store it in the queue, doesn't make sense. It doesn't make sense as a start. All right, so you have to be clear about the use cases. And if you're expecting that, yes, the scenario for this data will always require that, okay, at every point in time, you need to know what is the minimum value or element, or you need to know the maximum value or element. Yeah. So that structure becomes an essential element of making your search very efficient. Okay. Then note the separation between the keys and values. Again, we'll come back to this under binary search trees. It's very important. In some cases, your order should matter. Sorting, okay, sorting is very, very important. Then understand the tree structure. That's again talking about binary search trees. Okay, very important. On this note, your data features, your characteristics of your data is very important. Where it's important because in the case of min and max determination, you do not need a search, right? If your use case is that you want to easily know the minimum or the maximum element, you can structure your data to bypass search altogether. And that's a consideration. If that is a major use case, then your data should be structured that way. In that case, you are looking at a min heap or a max heap data structure. Okay, so that is very important. Then furthermore on the searching assumption, searching is that keynote to note is that your search assumptions are built in your data structure. So all the data structures we've looked at so far already contain information about how you get an item from them. And in each discussion, we talked about iteration. In some cases, we show sample codes for iterating each of those structure. How do I iterate an array, stack, linked list, matrix, tree, graph, like very important. And then pay attention to the shape of the underlying structure in terms of the order. Again, talking about the success, then sorting, and then not just the sorting, the relationship. So if you pay attention to relationship in some cases, that will determine whether you use a linked list for your data structure or you use a tree. Okay. So if you want to position your data, if you want to arrange your data for efficient iteration, that you want to get out of your storage sorted data as fast as possible. Okay, you want to maintain relationship and you want to get your data in a sorted order as fast as possible. That will determine whether you use a tree or a linked list. Both of them have assumptions about relationship. Okay, a linked list points to depending on the type of linked list, it could point to a parent, it could point to a child. Okay, so but if you want sorting, okay, in this relationship, then a binary tree will be better than a linked list. Okay, so understanding that kind of relationship, the nuances among this data structure, and the relationship embedded in them is very, very important. And related to the uh, relationship is also directionality. How is your data moving? As you store your data, do they contain forward or backward movement? So you determine in some cases that a doubly linked list, okay, is better than a simple list. Or you determine that your data should be stored as a graph, okay, to show which vertex or vertices, which vertex connects or leads to another vertex. All right. So the direction, relationship, and order of your underlying data structure is very, very important. Yeah. So your keys can be maintained differently from your actual data. This is saying the same point again. Oh, okay. So you see this for hash table and even in binary trees. Okay, and it is the basis for their efficiency. There are many searching techniques. We are not going to talk about all of them today. We are only going to focus on two. But there are many of them. Their performance varies. Note that there is no perfect strategy yet. Okay, it's still an ongoing exercise to find the magical search algorithm that will rule them all. So going through types of searching, remember we mentioned that there are many more of them, but we will just focus on the two general methods, okay, which are grouped under linear search or binary search. Okay, so these are very, very important. Just bear this in mind. Note the type of search you're going to perform. Uh, the simplest type is the linear search. As a name portends, you go from index 0 to index n, whatever it is. Okay, so that search goes through all items in your list or your storage. Okay, you should be able to do that. Iteration is simple iteration. Okay, your simple while loop or for statement is a linear or can just give you a linear search. There's not going to be any skip. You're not skipping. The assumption is that you are not skipping any item as we go through the list. Okay. Now, this type of search is usually required when your data is not sorted. That is random. Okay, so for unsorted data, okay, for unsorted or random data, you are forced to do a linear search or a sequential search. Okay, so that is why we mentioned that sorting or the knowledge of the sort order of your data is important. You should be clear, okay? You should have evidence. Either you are told reliably or you have evidence given sample sets to see that, oh, this data is not sorted. So at that point, you are forced to consider a linear search. Okay. And when you do a linear search, you are, by implication, you are confined to the order of your data or to the number of items in your data. Okay, so we'll talk more about this. But among these general methods, the most efficient ones, which we'll talk about also today, will be this one. I just purposely put this one here so everyone is clear about this. Methods for efficient searches as at today, okay, are around these four techniques. Okay, if you gather different thoughts and opinion here and there, you'll not hear anything more than binary search tree, red flag tree, uh, or AVL tree, binary tree, a binary heap, and a hash table. Okay, so uh, all these, apart from hash table, are still some form of binary search. Okay, but note that generally, this is important. You are either doing a linear search or you are doing a binary search. Okay, very important. In most cases, to get performance, you should consider this, the binary search engine. Yeah. So your sequential search is linear, right? Going through all the items required when your data is unordered, whether it's a list, stack, queue, whatever it is, there is no sorting assumption. Okay, this is what you are forced to use if your data is in random order. You start from the beginning to the end, checking all elements. So if you are going through it, you are going to be comparing input, your data input with the key. Like, oh, at this point, does this mean this thing? Is this what this means? You have to consider that. Okay, for each element, imagine doing this for 10 items, not a problem. 200 items, not a problem. As your data grows, you begin to have a problem in terms of performance becomes low. Okay. I think there's a hand raised. Ayobami.
It was a mistake, sir.
Oh, okay. All right, no problem. All right. So that's something to note for your sequential search. If it's a subset of data, it is not a problem. What I mean by subset of data, a small subset within a large implementation, you are searching a small, or you have to iterate a small amount of data. Of course, that's not a problem. In the other search type, like binary search, you could iterate 3 items, 100 items, okay, out of maybe 10,000 items. That's not a problem. Okay, it's a different case if you have to all the time iterate all the items to get an answer. That is where a problem is. Okay, so sequential search checks all the items. It is naive. Okay, if you have to, that's if you have to go through all the items, we call it a naive solution. Okay, so you want to steer clear of this as much as possible. Steer clear of going through all your records. At best, any greedy or brute force technique may be more efficient, all right, than this. Anyone at all. We'll talk about the greedy and the brute force, the greedy, especially the greedy technique. The the simple way to think about the greedy technique is that you make a definite choice about where to search. Okay, rather than search from the beginning and go all the way to the end, you make a safe choice that I think this value will likely be from number 40, and then you start your search from 40 all the way to, if you say, oh, if you think, okay, it can't go beyond 80. So you start your search from 40 and you stop at 80. It's greedy. It could be safe, all right, because you have other information about that environment to be sure that, yes, this data cannot go outside this bound. So you know that it's between 40 and 80. You just search, you do a sequential search for 40 to 80. That way, you have reduced your response time because you are not searching the whole item, So that is greedy. And the point is that even that greedy solution is better than the naive approach of a sequential search. Okay, so note that in mind. Rather go greedy and be safe than be naive and things just blow up. Okay, so in terms of its runtime, if you are extremely lucky, and luck is a strong word here. If you are extremely lucky, your best case will be a constant time of 1, okay? But your worst and the average case will be big U of n. That's meaning is going to run in linear time. So linear operations for 100 records, not a problem. With the computing resources available nowadays, 1,000 is not a problem. As we begin to grow, maybe 10,000 is even not a problem for what we have right now. But as your data begin to grow and other operations depend on your data, all right, remember, you are not only just titrating the list and then maybe doing a simple operation like printing, all right. You are iterating the list. As you iterate a list, you perform other computation. So if you think about it holistically, as your data grows, a sequential search is problematic. Problematic for all kinds of like useful cases you can think of in the current environment. There are about maybe 6 billion people or accounts, 6 billion accounts on Facebook. That's the meta group of companies, including Facebook, Instagram, and Threads, the new app, right? Imagine running a sequential search through all the accounts. Okay. Yes, we could say Facebook has the computing resources, they have supercomputer also. That is not a good solution. You can't run the sequential search. So certain algorithms have to come in to make searching for an account as fast as possible. Something other than a sequential search. Okay. So it's simple. This is just a sequential search in a pseudocode. It's a simple search where you have a list, in this case, an array. You start from the first to the last using a particular key. Okay, and as you go through it, you're doing a comparison. Is this key available at this index position? If it is, yes. If not, you return a -1. Oh, okay, so very simple. Just be able to do it. Just note it. Okay, but you may not need it. No. So the central question in computing posed is, are there algorithms or data structure that achieve logarithmic performance for both search and in search? Now, this is important question before we go into binary, and is to put binary search in context. Okay, we are done with sequential search, just for knowledge sake. Okay, to know it and its characteristics and the problems it posed. Okay, it is not a useful technique in computing. So the problem that drives innovation around search is this question: what algorithm and what structure? Remember, it's not just algorithm. That's why I'm projecting this question. It's not just, okay, what algorithm do we need that will optimize our search and insert? It's saying what algorithm and structure. That's very important. So I think this should be underlined. The algorithm and the data structures that should be combined to achieve that. So that we don't have to go through all the items. And that's where the logarithm aspect comes in. All right. Remember the concept behind a log or a log uh, operation. Okay. The idea is that you don't have to go through the item. You divide by a number, and you think about how many times can you divide that number to reduce the number of iteration. Okay, so insert is also important here because as you store your data, in some cases, you have to maintain a consistent structure to keep optimizing your search. That is the idea. That's also why search is insert is problematic. Remember, we mentioned earlier that change operation is expensive. It's a problem. You insert, you add a new record, you delete a record, you have to think about the implication. Are there gaps in memory? If it's a tree, do I want to keep the tree out of shape or to keep it balanced? And if it's a linked list, you also have to think about that, not reference. Okay, so insert comes with its own headache as much as deletion also do. Right? And it is the answer to this question that leads to this solution. The two fundamental solutions provided for these answers are binary search tree and the hash table. Okay, very important. The binary search tree, that's the most fundamental algorithm in computer science. There are many other algorithms here and there, much more complex. Okay, but this BST alone is very important. At best, it ensures that we don't have to go through all the items. Okay, so we'll talk about the binary search tree. Okay, and then the hash table. Hash table is simple. Hash table, the best case scenario you could have, okay, just to quickly mention that that's the best case scenario where you do not have to do a search. You just compute a value and use that value to locate your item. So the performance of hashing is far better than a binary search tree. Okay, well, it comes with its own headache. All right, you have to compute. You have to ensure that your keys are uniformly distributed in your index table. You have to worry about gaps in that tree. You have to worry about conflicts and their collisions. No, all right. But where binary search tree comes in is that it combines the efficiency of a search, of your binary search. Okay. The efficiency of your binary search with the flexibility of your linked structure. So it uses linked structure in a way. Oh, okay. So your binary search with some sort of keys through hash table are maintained in that way. All right. So we'll go ahead with this and talk more about that binary search. Yeah. So you see binary search and binary search trees in discussing trees last week. But just note the basic idea is the basic idea is just that you obtain your data items, okay, and maintain them in a particular structure, in a tree structure, okay. Once you have them in that tree structure, your search, you can then begin to search that tree. Oh, okay. And as you are searching the tree, the assumption is that you are not going through all properties. You are not going through all items. Depending on consideration, like, okay, if the data is greater than if the value is greater than the node value on the left, then I go left. If it's lower than the value on the right, then I go right. So that alone begins to cut off your search parameter or your search perimeter, the areas where you search. That as you go to from each layer, as you come down each layer from the root and make a decision that eliminates search along that layer, then you go to the next layer, make a decision, eliminates an other item search, you're already getting a log performance. You're already in the log of n scenario. So that is the idea behind binary search. Okay, you break your stuff, you break things into two. Is similar in the context of divide and conquer algorithm. Okay, when we talk about, we'll come back to divide and conquer algorithm in 2 weeks' time. Okay, because as you move up, you're already breaking up your solutions into sub-problems. You are breaking up your problems and coming up with sub-solutions. Right. So this consideration already makes your binary search faster, much more faster than your sequential search. So that if you look at this table, all right, you could see that your search usually will start at the midpoint of your record, and then you begin to determine whether you go left or you go right. And as you go left, you check middle position again, rather than move from 12 to 8 to 5 to 2. You check middle position, then check another middle position until you get to the solutions. Yeah. So the for binary search to work, it requires that your data is ordered. Okay, so the ordered list data structure is what will give you this performance and boost and benefits. You can't use it if your data is random. All right, because really you are going to, at that point, you are actually going to get linear time. You can't use it. Okay, so this must be sorted. Then, because remember this point, at the point of insertion, you always maintain the data structure. So data will be sorted. As data is added into your items, it has to be structured. And that is the idea behind keeping a binary search tree balanced. Okay, it has to be balanced through mechanisms such as maybe you want to manually reorder it upon entry, or you implement you go for the red black trees, which is self-balancing and tree. Okay, so data has to be sorted all the time for this to work. Okay, it just means that when data is inserted at a particular position, okay, even when inserted at the end, then the whole trees need to be rebalanced. Yeah. With the midpoint search or with the midpoint searching, you find that half the search space is already eliminated. I mentioned that before. Okay. Yeah, and it's a technique, is actually much more related to the divide and conquer technique. Okay. So the major challenge with this binary search technique is the extra cost, okay, of sorting at insertion. Okay, that you'll hear more about that next week when she talks about sorting. Oh, okay, as you keep your data, as you manage your data, and as more data come in, they have to be sorted. So there's an extra cost that is required to maintain a binary search algorithm. Okay, but even at that cost later, you still get this log of n, big O of log n, okay, which is good. All right, so rather than a linear time, we got a boost in your response time. And remember, you talk about just a log of if you have 10,000 data points, and you want to search an item that has 10,000, a list that has 10,000 items, with BST, with sequential search, you are going to go through it 10,000 times. With a binary search, you are going to go through the list, guess, 4 times. That is a big difference. All right. Again, with binary search, with sequential search, you expect 10,000 iteration. Okay, 10,000 comparison. With binary search, it's just 4. So that is why it's very, very fast. I mean, log of n, very, very fast. Okay, don't mind that searches and inserts are mixed. That is the only drawback. Okay, but the benefits sort of outweigh the cost of doing it. Okay, and this is why many searches nowadays are extremely fast. Okay, so here's a pseudocode for binary search. Okay, irrespective of language, this can be implemented in any language. It assumes data is sorted. Oh, okay, so you have an idea of the left position, and you have the idea of the lowest position, which is on your left, and the highest position, which is on your right. And then for each operation, you are searching the middle point. Okay, so if you get the middle of the left plus right divided by 2, you check data at the middle point. If it is less than what you're looking for, okay, you go left. If it's greater than, you go right. Okay, and then you compare value at that point, which returns either true or false. Oh, okay, so this is why this binary search is so much important. It's an important concept in computing. Very, very important. It doesn't give or sequential search cannot reliably give you anything better than this. Okay, cannot. The only thing that beats this again will be hash table. Oh, okay, yes. That's the only thing. Okay. But a hash table doesn't give you relationship and some sense of direction, which BS binary search can give you. Okay, so binary search is very, very uh, important here. Yeah. And then in binary search discussion, you see some differences between BST itself and then binary heap. Okay. BST, that's your standard binary search tree. And then there is also this binary heap, a little different, but apart from that, they are usually the same. Okay, so I project the differences here where in your BST, you have your keys and your values, which is based on the linked list and the heap structure. Okay, your binary heap doesn't separate between your key and your value. Everything is just stored uh, as an array. Okay, in that case, it's not ordered. All right, that's another thing about the binary heap. Okay, so why I'm projecting this is that even if, depending on the scenario, the data is random, okay, one can look at how you can put that random in a binary heap structure. Okay, remember heap. Okay, so you put that in that context. If you put it in the binary heap structure, your random data, you put your random data in a binary heap structure, you could get big response. Okay, big uh, response or runtime, like a much more efficient runtime for your search, for your insert. Okay, so uh, uh, that's just something to consider. In some cases, for BST, yes, in your binary search tree, you can't have a duplicate. All right. So again, the another reason for projecting this is depending on your use case scenario, you can determine whether you want to go with BST or a binary heap. All right. So for this can allow duplicate. The other doesn't allow duplicate. Okay. It requires extra storage because it uses pointer linked list. As long as you use a linked list, you're going to rely on referencing. Okay, it uses pointer. Yeah, so but this combines linked list insertion benefit. The greatest benefit of linked list is flexibility for insertion. You don't have to rebuild the array. Okay, in this case, you have to rebuild the array when you add a new item. Even though rebuilding the array uh, can give you maybe a linear time. In some cases, can be an issue or not an issue. Look, okay. But to make BST much more efficient, all right, than binary heap, to make it much more efficient, the tree has to be balanced, which is why red-black tree is superb in performance. Is always balanced. Once it's balanced, as long as it's balanced, you will get a big O of log n. All right, for your search. Okay, so for BST, you have to ensure that your tree is balanced. Okay, ensure that it is balanced, and then it outperforms binary heap in that if you have to get your data in a sorted order, your data already is sorted. So you can get all of your data sorted in linear times. Like just go through, just iterate or traverse the whole list and you have sorted data. You don't have to do any exchange, any comparison, nothing. Out of the box, everything comes out and sorted. So again, showing the power of BST. Okay, so it's just important to note that difference. Okay, then with that difference and talk on BST, we just have just one slide. Hashing is simple. We discussed hashing under data structure. Okay, in the context of search, what you just need to know is that it does not require sorting. Okay, you don't have to sort the data. You have to maintain an index table or a symbol table. Or okay, yes, that is important. That's the basis for hashing. You have to maintain a separate table, like an index table that tells you the location of the data. Okay, works well with all data structure. And for now, it is the fastest algorithm because it gives you constant time. Okay, fastest, right? Comes with headache. It doesn't have directionality, relationship, and then sorting, which you have in BST. Okay, so in most cases, your BST may be used. All right. So here is just a table to show all those things we've been talking about, from sequential to binary search on ordered data, binary heap, binary search tree, and then the hash table. So as you can see, the hash table seems to have the best performance. Okay, but for this, BST comes with much more benefits. You can get sorting, you can get your floor or your ceiling in log of n times. You want to find in some cases where an element is, I think it's actually much more, it gives you much more functionalities than your hash table. So, okay. Your binary heap, okay, I forgot to mention something about binary heap, which also makes it very useful. Because your binary heap still maintains the idea of minimum min heap or max heap. Okay, if you want to get the minimum element or the maximum element, you don't have to search. You just get it. All right. So that is one advantage binary heap probably have over BST. They are all, you can search, you can see they are all in the log of log n runtime. Okay, but for min and max element search, that would be binary heap. Binary heap will give you constant time, whereas BST, you still need to do some search. Okay, although still fast. Yeah. Let me take some questions. I think we are running out of time. This will be the last session. The last session will just be to give you pseudocode. It's just a set of pseudocode for searching various types. Let me see, are there questions before I take this last session? We should be done in maximum 10 minutes. Any question? Okay. Okay. If you have questions, you can type in there while I continue. Okay. So quick considerations for searching based on data types, your data structure. Very quickly, if you are searching an array, these are just a set of rules. Okay, just bear them in mind. If you're searching an array, the assumption here is that the array is sorted, though with binary search. Okay, and this is the pseudocode for it, and some text, explanatory text alongside it. Okay, so your binary search is useful for an array. For BST, yes, depending on how it is stored, okay, you could get a linear time if you are going to do a search, because you go through everything, all right? But you could also still use BST if there's some sort order for your linked list. Okay, so the binary search tree algorithm can be applied on a linked list. The basic principle just being that you always search in the middle, which is why you find the middle element of the linked list, and then you begin to go downward. Like as we move to the next middle, we move to the next middle until you get your data. But the issue with linked list alone is that the performance of BST is wonky. That is not really beneficial for linked list. Linked list with BST is a problem. It still gives you linear time. Which still means you're going to search 10,000 times. Okay, which is why the binary search tree, remember the binary search tree combines linked list with heap. All right, so that improvement is what you should look like. So as much as possible, think rather than just go with linked list, think binary search tree. All right. For stack, your stack data structure does not benefit so much from any search algorithm apart from the sequential search. Okay, so your rack of plates, you want to go through them, or your stack of plates, you want to go through them, you have to keep popping out each plate or each item from your stack, one after the other. This can benefit from dynamic search tree alone, okay, because you always go through each item. Okay, you always go through each item. If you combine this, if you combine stack with hash table, okay, yes, that will tell you the position. Okay, it tells you the position. But iteration, there's no way you still have to just go from the last one in to the first one out. So note that limitation for stack. It also applies to queue. You have that limitation with queue. Okay, these are not really optimized for search. So something to bear in mind, they are very useful. We'll see later in divide and conquer and some other tests how that you use them as a in-memory, temporary storage, like to keep a list of RPs as you run an operation. Okay, for instance, if you are going to get a reverse order of a string, okay, that information will be stored in a stack. Okay, so that the last one in, okay, becomes you have a LIFO structure. Okay, last one in, first out. Okay. So they are still useful, but they don't benefit from your binary search tree as much. You have to build other layer on top. Yes, searching a matrix has its own challenges also. Okay, so a matrix, the best performance I've seen from a matrix search is big O of n plus n. All right, which is better than what a sequential search will give you. A sequential search will mean that you go through all rows and all columns, and along these dimensions, you go through all cell. Okay, so you iterate all the cells. So if it's a 3 by 3 matrix, it still means you're going to go through the 9 cells. Okay, so that will give you the sequential search there will give you n times n runtime. But this algorithm here, okay, will give you something better, n plus n. Binary search doesn't give you much here. The runtime is around n multiplied by log of n. Okay, so the use case here is the usefulness of binary search has its own limitation here. Remember what we mentioned at the beginning on algorithm. Algorithm has scope and limitation. So note the limits of the algorithm. So such that even as BST is a superb weapon, it does not scale with certain data types. Okay, so linked list, matrix are some of them. Yes. The best you can get from the graph data structure is your vertex plus the number of edges, okay, that lead to the points in your graph. Oh, okay. It's still good, okay. It's a greedy algorithm because you always have to start from somewhere. You know a place to start from. All right. Again, this can benefit so much from BFS. BST. Okay, so you are starting from a path and you search from there to the next path until you get all the paths that are visited. Look through what is, we call them adjacency list. You go through what is beside, what can lead from one node or from one vertex to another, and then you store them. So the big notation for that is not usually less than this. Okay. The same thing you can use for the graph. You can use either your depth first search or your breadth first search. She talked about this just last week. Okay. Again, the complexity is not more than this. Okay. Yeah. Okay, I think this is where we'll stop today. Problem solving. This is where we'll stop today. The summary of what we've said has been your data structure, the order, and the format, and either you maintain a symbol table with a hash table or you use a binary search. These are some of the most efficient search algorithms that we talked about: a hash table and then binary search, a balanced binary search based on a balanced tree or a self-balancing tree, like a red-black tree. So, okay, so we'll stop here today. Let me see, are there questions? Okay. Okay, so if there are questions, let us know in the stack. Yes, well, let us know in the chat, and then we can discuss more. Also, you can leave your comments or your questions in the Slack channel. Okay, so next week there will be more on sorting, and then we'll go back to divide and conquer, where we'll also still talk more on the binary search tree. Okay, but the major point for today is, in terms of searching, you have a super ally binary search tree. Thank you, everyone.
Thank you so much. Thanks so much, Saji. Thank you, everybody that has been in this class. We've learned a lot, and I'm sure so many people have learned. I'm sure we're taking it all in. So, in case you still have questions after now, like let me say you trying to get things, and then after this call you still have questions. Okay, I think there's a question in the comments box. Okay, is there? Shema is asking, is there a difference between binary search tree and binary tree? So,
Yeah,
Saji.
yes, yes. So they are usually used interchangeably in such a way, like in some cases, your binary tree is the structure, okay, uh, and your binary search tree is the algorithm. Okay, but usually you can't separate it. Last week, you talked about the binary search tree, okay, as part of the tree. Okay, so some will call the tree itself binary tree. And then when it comes to searching, some will say binary search tree. Oh, okay. So uh, I think is a challenge with naming things properly in computing, but see them as two sides of the same coin in the terms of structure and the algorithm, but not much different. So binary tree, look at it as structure, or call it simply tree. Okay, binary search tree, look at it as algorithm. But then some will call the binary search tree binary search, and then further break down binary search into things like binary search tree, binary heap, uh, red black search tree. Okay, yes, so it can be confusing, but just note how it works. It's all that matters. Thank you.
Okay, makes a lot of sense. Shema, are you okay with that answer?
Yeah. So the reason I asked was because in one of the slides that was used, where a comparison was made on the time complexity for uh data structures, I saw that there was a binary search tree and then there was a binary tree, if I except that I didn't get it correctly, and they had slightly different performances. So that's the reason I asked. It wasn't very clear.
Okay, is it in the slide, my slide for today?
Yes, yes. In one of the slides where you had
Okay,
binary heap, binary
okay,
search tree, hash table, and all those things in a
okay.
tabular format.
Let me share my screen again. Okay. So this one, right?
Yes, this one.
Okay. Okay. Yes. So yeah, that's part. This is it. Okay. So the binary search here, all right, is the assumption, based on the assumption of an ordered data, uh, in especially say array. Okay. That if you have, it's a generalist approach here, where you're saying if you have an ordered or sorted data, you can use a binary search. It's a principle here. Any ordered data, will give you. If you run binary search on any other data, you get big O of log n. Okay. Now that is different from if whatever your data is structured as a binary heap. Okay, you still get this. Anything that is based on binary search, whether it's a variant of BST or binary heap, will always give you log n. So this is just me focusing on any other set of data here. But look at this as anyone that is, it could be a list, it could be even a stack, though BST binary search is not optimized for a stack, but if you take a stack or a queue and then move the data into an array other than in an array, then you can get the benefit of a binary search on that. Okay, but if your data is structured as a heap, all right, binary heap, because there's a heap structure, min, max, each node having subnodes, each subnode having their own subnodes to each, right? You have the benefit of a binary search. If your data structure is based on linked list plus heap, then you have binary search tree algorithm. Any of those variants will give you this time complexity. Oh, okay. Yeah. Does this clarify it a bit?
Yes, it does. Thank you.
All right. Thank you.
Okay, thank you. Thank you, Saji. And thank you so much for the question. It has created clarification for that aspect. Is there any other question? Does anybody have a question to ask before we? Yes, and to mention, the feedback form is in the comment section. So I pasted the feedback form. Just click on it and fill in the feedback so we can know how you feel about the bootcamp and how it's going from your end, and if you need any further help. Just click on it and fill it up. Yes. So if there are no questions, just a quick reminder: your assignments, the weapon, and everything would be sent via email. However, the Slack group is available for communications. You can communicate with everybody there, the leads, your colleagues, like everybody on Slack. And also do not forget to practice. That is all you need. Practice, practice, practice. If it's confusing, if the terms are still confusing, keep practicing. Consistency will always win. Don't forget that consistency would always win. Okay, thank you so much. My name is Buchi, and with that, we've come to the end of today's session of our
Sorry,
DSC. Okay.
sorry to chip in. Yeah, I've been like uh wanting to ask if you could like resend the Slack link, Slack group link.
Okay, so
If
do
you
you
have.
usually get the mails?
Yeah, I do get the mails. Yeah,
So it's always in the mail.
for the RSVP,
No,
if
not
I
the
receive an RSVP.
RSVP. No. The
Okay,
mail that comes after each class. The mail would most likely come
okay,
tomorrow. So you get a mail, yes, you get a mail with details, and the details of the Slack should also be there. So just look out for the class
okay.
tomorrow. If you don't get it, you can still reach out. You can just drop a message on WhatsApp, and
She
then we'll still be
she
sending.
already sent it.
Sorry?
She already sent it to me. Yeah,
Oh, great,
she, al-
great, great.
she just
Makes
sent it
sense.
to me.
Okay. All
I
right
thank you.
then. All right now. Okay, so is there any other thing from anybody's end? All right, so everybody have a lovely weekend. Enjoy your day, enjoy your weekend, and do not forget that consistency wins. Bye.